Welcome everyone. My name is David and I will be doing this lecture today on lab techniques and applications. So like I said before, this lecture is being recorded and will be posted on YouTube. It's just a release form saying that you are aware that we are recording this lecture and we'll post it on YouTube. So if you want to change your profile picture or your name on Zoom, you can do that. It's just a small summary. And if you want to see the full document, you can use that link at the bottom. So just a quick description on the course. This is the 15-week MCAT course, MCAT program. We do lectures on Zoom every Thursday, Friday, and Saturday at 8:30 p.m. EST. And on Sundays, every Sunday at 8:30, we'll also be doing office hours. If you have any questions or need any general advice, you can come through it and we can help you out. Just some useful links. So if you're not part of the group meet chat, you can use this link and join. Oh, sorry. You can use this link and join. There's other students and tutors in the chat, so you can ask any questions. And we do have a YouTube page, like I said, if you want to check it out. We post the recording of the lecture, so if you want to watch it after the lecture, you can do that. And we also cut up the videos into smaller videos on specific topics, so you can check that out as well. We do have a website, socraticmed.net. I believe it's still currently down right now, but once it's back up, you can check it out. We have useful links on there and we post updates as well. And so our Instagram page, you can give that a follow if you want like daily reminders and updates on the program. So going to lecture, just some learning objectives for today. I'm going to go over a few lab techniques that are used in chemistry lab and biology lab. So I'm going to go over extraction, distillation, filtration, gel electrophoresis, and chromatography today. So first lab technique I'm going to go over is extraction. So extraction is used when you want to separate out a desired product from a mixture. So this is when this is used most commonly when you're trying to separate polar and non-polar compounds. This is used in organic chemistry lab. So what you do is you transfer the dissolved compound from the starting solvent into a solvent which the compound is more soluble in. So the desired product that you want may be mixed in with other solvents, and in order to separate it, what we do is we use a solvent that the desired product is more soluble in order to extract it from that original solvent. So most likely the two solvents are immiscible because if you have a polar and non-polar solvent, the two do not mix. And this forms two layers that are known as immiscible. So you can see that there is a divide between them. They won't mix together. And like I said before, in order to extract the solvent, extract the desired compound, you use a solvent that the product is more soluble in. So if you are trying to extract a polar substance, you will use a more polar solvent in order to transfer the polar substances from the starting solvent into the new more polar solvent. And likewise, for non-polar substances, you will want to use a non-polar solvent in order to transfer the desired product into that more soluble non-polar solvent. So for polar solvents, most of the time water is used, and that polar solvent is called the aqueous phase. So aqueous sounds like aqua, which is water. So aqueous phase is the polar solvent, and for the organic phase, the non-polar solvent is used, and the most common non-polar solvent is ether. So make sure to distinguish that the two phases, aqueous phase and organic phase, those are the two solvents that are immiscible. One is polar, the aqueous is the polar solvent, and then the organic phase is the non-polar solvent. So these two will be in the separatory funnel, and you will extract the desired product by mixing the two. So because one solvent is nonpolar and one is polar, they can't be mixed, but you can temporarily mix them by shaking, so the solute passes from one solvent to another. So even though you can shake it and mix it, because of the difference in polarities, they won't permanently mix. So you can shake it, but after a while, if you let it settle, it'll separate again. It's like if you mix polar water and then a non-polar substance like oil. If you put the two in the same container and shake it, you can mix it for a little bit, but after a while, it'll separate again. So we use this property in order to extract the desired product. So like I said before, in order to extract the desired product, we use the solvent that is more like the desired product in order to extract it. So if the product you're trying to extract is a non-polar substance, you will find the product in the organic layer, which is the non-polar solvent. But if you're trying to extract a polar substance, then the polar solvent in the aqueous layer will contain your desired product. So by mixing the two layers temporarily, the desired product will either, if the product is a non-polar substance, by mixing it, you will transfer it from the aqueous layer into the organic layer. And the opposite will happen if you are trying to extract the polar product. So the organic layer that originally had the polar substance will transfer it to the aqueous layer after mixing. So on the right, I have a picture of a separatory funnel. So this is the equipment used for extraction. Organic layer will be on top and the aqueous layer will be on the bottom. So you'll put the two solvents through the top of the separatory funnel, and the stopcock on the bottom will allow you to release the solvent. So if you're trying to extract the polar solvent, it will be in the bottom layer, the aqueous layer. And so you will keep that. But if you are looking for a non-polar substance, you will discard the first aqueous layer, and then you will keep the layer on top, which is the organic layer that has the non-polar product. Like I said before, the aqueous and the organic phases will separate on their own after some time. So after shaking, if you let it settle, the two layers will separate. So the separatory funnel isolates the two phases using gravity. The denser aqueous phase will be on the bottom, and the lighter organic phase will be at the top. So you can repeat the extraction multiple times. So in order to get as much of the product as you can. So you can keep adding either more organic phase or more aqueous phase, depending on which product you are trying to extract. So if you're trying to extract more, if you're trying to extract a non-polar product, then you will keep adding more organic solvent and extracting the organic phase. But if you are trying to extract a polar product, then you will keep adding more polar solvents and then keeping the aqueous phase. And after you're done extracting as much of the product as you can evaporate the excess solvent using a rotary evaporator, also known as a rotovap, to obtain the product alone. So because you use the solvent to extract the product, the solvent will be mixed in with the product that you extracted. So in order to get rid of the product, you will use a rotovap to evaporate the product. So you only have, rotovap to evaporate the solvent. So you will only have the product at the end. And the picture on the right is just a depiction of that extraction method. And then, so there's also a technique known as wash. So this is the reverse. It's kind of like the reverse of a extraction. So this is used to remove impurities. So what you do is you use a small amount of solvent to extract the product and remove the impurities. So that is that's not the desired product. So basically, you're washing your solution in order to remove the impurities. Any questions on extraction before I go into a question? If you have any questions, you can unmute now or put in the chat. Mark, the other tutor, is here to help if you want to put in the chat. If no one has any questions, I'll give everyone this problem. So like I said before, ethers are generally effective solvents for organic molecules because, let me start the poll. I'll give everyone a few minutes for this question. All right, I'll give everyone a few more seconds for this question if you want to put in your final answer. All the answers are anonymous, so put in your best guess if you don't know. All right, I'm gonna end the poll now. So most people chose choice C, and yeah, that's so the answer is actually choice D. So ether, like I said, organic solvents are non-polar. The polar solvents are the aqueous phase, or the polar. So the polar solvents are the aqueous phase. Ethers, they're organic molecules, so they would be in the organic phase, which is the non-polar solvents. It would be choice A because you don't want it to react with the reagents. You want it just to associate with them so you can extract it later. If you react with the reagents, then you'll get a completely different product. And they won't, they're not solvents for organic layers because of hydrogen bonding. And like I said before, they're non-polar molecules, so they would not be polar. Does anyone have any questions on this problem? If you have any questions, you can unmute or put in the chat.
Just as a clarification, sorry, I had a question like why it's non-polar. So is it because like it's like a symmetrical molecule, so it's like not polar?
So ethers, they're mostly made up of like long alkyl chains full of carbons and hydrogens. So that would be non-polar. Most of the polar molecules are like alcohols, carboxylic acids, amines, stuff like that with like electronegative elements that will make it polar. Ethers, they're mostly like long chain carbon chains, so that would be non-polar because of all those carbons and hydrogens. Does that make sense?
Yeah, that makes sense. Thank you.
Okay, no problem. Anyone else have any questions? Okay, if not, I'll move on. So another problem, when would it be appropriate to use extraction in order to separate compounds in a solution? All right, take a few minutes to read this, and let me start the poll again. Okay, all right, take a few minutes to read this problem. All answers are anonymous, so please put in your best guess if you're not sure, or click the last choice. I'm going to stop the poll in a few seconds if you want to get your answer in. All right, I'm going to stop the poll now. Everyone picked choice D, and yep, that's the correct answer. Yeah, so for extraction, you want to separate compounds that have different polarities. So if you want the compounds to have different polarities because of the solvents you use. So because you use a polar and non-polar solvent, you want the compounds to have different polarities in order to separate them. Extraction wouldn't separate compounds depending on their molecular weight, solubility, or double bond length. So extraction used for different polarities. That's the key point to get out of this. Any questions on this problem? Okay, all right, I'll move on to the next thing. So next, I'm going to go over filtration. So filtration, this is used when you want to isolate solid from liquids. So on the right, I have a picture of a gravity filtration. So the basic concept of filtration is when you have solids mixed with liquids and you want to separate the two, you'll pour the solid liquid mixture onto the paper filter. And because of the filter, only the solvent will be able to pass through. So the solid will get stuck on that paper filter. So that separates the liquid solution and the solid in that solution. So the solid that is left the solid that is left behind is known as the residue, and the filtrate is the liquid that passed through the filter and went into the flask. So this can be modified in order to filter either the solid or the liquid. So depending on if you're interested in the solid or the liquid, you can modify the filtration in order to get the desired product. So there's a few different filtration methods. So like I said, that first picture was known as gravity filtration. So it's known as gravity filtration because you use the weight of the solvent to pull it through the filter. So gravity will drag that liquid solvent through the filter, but the solid will be left behind as the residue. So this is used when you're interested in the filtrate and not the solid that's left behind in the paper filter. So usually you want the solvent hot in order to keep the product that is dissolved in the liquid solution to remain in solution and not get stuck on the paper filter. So this is known as gravity filtration. It's like the most basic way to filter between liquids and solids. Next, vacuum filtration. So this is the picture on the right. This is used with a vacuum. So the solvent is forced through the filter by a vacuum that is connected to the flask. This is used when the solid is the desired product. So you use vacuum filtration because the vacuum will suck as much of the fluid from that filter. So because there's a vacuum seal, the vacuum will suck as much of the liquid off the paper filter and off the residue into that flask and leave as much of the solid residue behind. So instead of just allowing gravity to filter it, you use the power of a vacuum to suck as much of the liquid as possible. So usually you'll use this when you want the solid residue as the product. So that's vacuum filtration. So there's a step called recrystallization. This is used when you want to further purify the crystals in the solution. So because the initial product that you obtain is impure, there may be like other stuff mixed in with your product. So what you do is you dissolve the product in a little bit more hot solvent, but then you let it recrystallize as it cools. So the solvent that you picked should only allow the product to be soluble at high temperatures. So because the product is only soluble at high temperatures, when the solution cools, the product will recrystallize out of the solution while cooling, but the impurities that are soluble at lower temperatures will remain in the solution. So then you can extract the product out of the solution as it recrystallizes and cools. So this step of recrystallization is very dependent on the solvent that's used. So the solvent that you use has to only allow the product to be soluble at high temperatures. So once the hot solvent is cooling, because the product is only soluble at high temperatures, once it cools below that temperature where it's soluble, it will recrystallize out of the solution, and that will be more pure than that initial product that you had. So because the other impurities are not only soluble at high temperatures, it will remain in that solution until the temperature is like way lower. So once you extract out that pure product, all the impurities will remain in that solution until that solution is cool. That's recrystallization to purify the product. So any questions on recrystallization or filtration before I give you another problem?
I did have a question. I was wondering, like, for sorry, the vacuum filter, or just the filtration in general, like, is there ever like I know, like, usually, like, for vacuum filtration it says like use when the solids is the desired product. Does that mean like for gravity filtration, would that be the same thing, or is there sometimes when you do want the liquid to be your desired product?
So sorry, can you repeat that again?
Sorry.
You say
Oh, sorry. No, I was just saying, you know how like for vacuum filtration, it says that it's used for the last bullet point, it says use when the solid is a desired product. So for like gravity filtration, is there ever a case where, is it the same case that you want the solid to be the desired product, or do you want the fluid or like the liquid to be the desired product?
So you can use it for either, but so vacuum filtration is better for the solid because the vacuum will suck out as much of that liquid as possible. So you'd be left more with more like higher concentration of just solid instead of like the liquid mixed in with it. You can, if you take the liquid from that flask, from the vacuum flask, it'll have the liquid, but it might have some of the solid mixed in with it because the vacuum might suck in some of the like dissolved solid. So vacuum filtration is better for solid because of the vacuum sucking out as much of the liquid as possible. And then for gravity, it's better for liquid because there's no vacuum, so all that liquid that goes through is liquid. None of less of the solid will pass through the filter in gravity filtration. So the concentration of the liquid will be more of the liquid product than the solid residue. If that makes sense.
Yeah, that makes sense. Thank you. Yeah.
No problem. Any other questions? Okay. All right. Here's another problem. So, which of the following statements about recrystallization is true? Give everyone a few minutes to read this. Okay. I'm gonna end the poll in a few seconds if you want to get your answer in. Okay, I'll end the poll now. So everyone chose choice B, and yeah, that's the correct answer. So yeah, like I said before, you want the compound, the product that you want to be recrystallized as it. Yeah, so the compound that's recrystallized is the desired product, the one that crashes out of the solution because of the solvent that only allows the product to be soluble at high temperatures, while the impurities still remain dissolved in the solution. And choice A is the opposite, so that's incorrect. Choice C, so the solvent is not completely interchangeable. Like I said, you need a solvent that only allows the product to be soluble at high temperatures. And then temperature is obviously, it plays a role in recrystallization. Any questions on this problem?
All right, I have one more question regarding this.
No problem.
Like for impurities, because it's been a while since I've done like my labs, but like impurities, is that usually like something like a different chemical that you're just not interested, or I guess like what would be considered an impurity?
Yeah, so impurity is just anything that is not that desired product that you want. So anything besides that product is considered impurity. So some solutions, some like reactions, it'll create different products. So some reactions you might get 70% of one product and like 30% of another product. So depending on which product you're in, the other one would be the impurity. And just because nothing is like 100%, you'll have like other stuff mixed in with it. So when you're doing experiments, that's why they have like percent yield. So like sometimes the stuff that you make is not what you want. So in order to separate the products to just get the one that you want, you have to separate out the impurities. So impurity is just anything that is not what the final product you want it to be is.
Got it. That makes sense. Thank you.
No problem. Okay. Any other questions or any confusion on this? All right, I'll move on to the next one. The next technique is distillation. So distillation is used when the product is the actual liquid that is soluble in the solvent. So this is when the product is soluble in the solvent, so you can't see, like you can't distinguish between the two liquids. So for extraction, because the two solvents were immiscible, they didn't mix. You can see like where they separated from each other. But this distillation is used when the liquid that you want is mixed in with a different liquid that you don't want. So you have to use this method of distillation in order to separate the two. So distillation, it utilizes differences in boiling points to separate the liquids. So this is done through evaporation and then condensation. So the mixture to be separated is placed in a distilling flask and then heated using a heat source. So as you can see on the picture on the right, the distilling flask, this will contain the liquid that you're interested in, and then also whatever solution that it's mixed in. You have a heat source on the bottom that heats up the flask and boils the solution. And there will be a thermometer attached because you want to monitor the temperature. So when you're separating the two liquids, you will have to know the boiling points of the liquids that you're that's in distilling flask. So you want to know the temperature because since there is a difference at boiling point, if the liquid that is distilled at like 37 degrees Celsius you will know what liquid that is. But when another liquid is boiled at like 80 degrees Celsius, that will be a different liquid. So you will know that there's a difference between the two liquids based on the differences in boiling point. So like I said, this is done through evaporation and condensation. So once you evaporate the liquid, it will go through this condenser. So this condenser is basically something that cools down the vapors of the liquid that you just boiled. So once it is cooled, it will condensate, and then it will drip down into this receiving flask. So this is basically the general mechanism behind distillation. Because the liquids in the distilling flask have a difference in boiling point, you can boil the solution, and the first liquid that comes out will be one distinct product, and then anything after that will be a separate liquid that boils at a different temperature. So the thermometer is important because you have to monitor the temperature at the temperature that the liquids come out in. The differences in boiling point is the deciding factor on like what the liquid comes out, what the identity of the liquid comes out is. So like I said before, the liquid with the lower boiling point will vaporize first. The vapors will rise up into the distillation column and into the condenser that is cooled by cold water, and the condensate will drip into the vessel, and that condensate, the liquid that comes out, is known as the distillate. So the temperature is kept low because you want to monitor the temperature, and you want to increase it slowly because the liquid with the higher boiling point, you want to ensure that it doesn't boil and remains a liquid. Because if the temperature goes up too fast, both the two different liquids will boil at the same time, and you won't be able to distinguish the difference between the two liquids. So distillation, as it's boiling, you'll collect the condensate, and the first condensate that's collected will be a distinct liquid, and then as the temperature rises, it will stop boiling the first liquid because it will all have been boiled and drip out as condensate, and the liquid left over in the distilling flask will be the other liquid with a higher boiling point that hasn't boiled yet, and will remain in the distilling flask until the temperature rises to that boiling point, and then it will come out as a condensate as well. So a key thing for distillation is you want to prevent super boiling. So this is when you heat the liquid too fast. It's heated above a temperature. It is heated to a temperature above the boiling point without vaporization. So this is when the temperature is heated up too fast, too high, and the liquid is above its boiling point, but nothing is boiling. So this is because the gas bubbles in the liquid are unable to overcome the atmospheric pressure and tension. So the solution will be at its boiling point, but not boil. So this is known as super boiling. And in order to prevent that, we use a boiling chip or a magnetic stir that you put in the distilling flask that like basically just swirls around in the distilling flask, or known as, there's also another thing known as an ebullator. These are used to break the surface tension and prevent super boiling. So it moves around in the liquid to break surface tension and prevent super boiling. This is important because if it gets too hot, the whole distilling flask will shatter. and your experiment will be ruined because this whole technique is based on boiling the liquid. So the different parts of the distillation technique, the distilling flask contains that combined liquid solution with the desired product mixed in with other solvents. The distillation column, it consists of the thermometer and condenser. So the thermometer is used to monitor the temperature of when the solutions boil. The condenser is used to cool the vapor and funnel it into the flask. And then the receiving flask on the other end will collect the distillate that evaporates and then condenses. So that first method I explained was known as distillation. There's a few different distillation techniques. So simple distillation, basically that technique I mentioned, this is used to separate liquids that boil below 150 degrees Celsius and then have at least a 25 degrees Celsius difference between the boiling points. So you use this when you want to boil liquids that have a boiling point below 150 degrees Celsius, and there's at least a 25 degrees Celsius difference between the boiling points of the liquids. So this is used below 150 degrees Celsius because you have to prevent the temperature from becoming too high, because when the temperature becomes too high, it'll degrade the compound, or the second compound that you don't want will boil off into the distillate because there is not a large enough boiling point difference between the two liquids. So you have to keep it below 100 degrees Celsius, and the two liquids must have at least 25 degrees Celsius difference between their boiling points. So that's simple distillation. There's another form called vacuum distillation or column distillation. So this is used to distill liquids with boiling points above 150 degrees Celsius. So simple distillation has to be below 150 degrees Celsius. When the boiling points are over 150 degrees Celsius, you have to use vacuum distillation. So a vacuum is attached to the setup. The vacuum is used to lower the ambient pressure to decrease the temperature that the liquid must reach to have sufficient vapor pressure to boil. So as you know, boiling is when the vapor pressure is greater than the ambient pressure. So the vacuum will lower the ambient pressure in order to decrease the temperature that the liquid has to reach. So basically, it will decrease the temperature needed to boil the solution. So this is good for any liquids with boiling points over 150 degrees Celsius, because if you boil over 150 degrees Celsius, the other compounds might degrade before reaching that boiling point. So vacuum distillation used for any liquids over 150 degrees Celsius. This is to allow the compounds to distill at lower temperatures, even though their boiling points might be higher. So that's vacuum distillation. And lastly, there's another form called fractional distillation. So this is when the liquids have similar boiling points. So the boiling points are less than 25 degrees Celsius apart. So because the boiling points are too similar, simple distillation and vacuum distillation won't be able to separate the two. So you have to use fractional distillation. So fractional distillation, it involves a fractionation column. So it's this long column in the middle with the little ridges in the center. So the fractionation column connects the distillation flask to the condenser. So it's basically simple distillation, but just with this extra column attached. So the fractionation column, it's used to increase the surface area to separate the liquids better. So this column will be able to separate the liquids in the distilling flask, even though they have boiling points that are less than 25 degrees Celsius apart. So how this works is when the vapor rises up the column, it condenses on those surfaces in the fractionation column and refluxes back down until the heat causes it to evaporate again and then condense again. But once it condenses higher in the column. So basically, it's repeated rounds of evaporation and condensation until it reaches the top of the fractionation column and then goes into the condenser. So this repeated evaporation and condensation, this is in order to separate the two liquids that have similar boiling points. So the vapor has a higher proportion of the compound with a lower boiling point each time the condensate evaporates and then condenses again. This is because the compound with a higher boiling point, it will take longer for it to boil and reach the top of the fractionation column, while the compound with the lower boiling point, it evaporates faster at a lower temperature, so it will evaporate more and condense higher in the fractionation column. So at the end, only the desired product with the lower boiling point will drip down the condenser and into the receiving flask. So that's fractional distillation. Any questions on this before the problem?
Yes, first, David. So they use the longer column to, let's see, why are they using you said to increase the surface area. Now, sometimes do they
sorry,
use,
Opal, I can't really hear you. Can you repeat that again?
let's see. Yeah, you said can you hear me now?
Yeah, yep.
You said they sometimes use a longer column to increase the surface area. So,
Yeah, so for fractional distillation, you mean?
Never mind, go ahead.
Sorry, were you talking about this fractionation column?
Yeah, so sometimes they use beads. Is that the same thing as increasing the surface area?
Yeah, so you see these like grooves in the fractionation column, those can be like made up of beads or they can add more beads in there. Yeah, so this is to increase the surface area. So when the compounds evaporate, when it touches these like beads or these grooves in the column, it'll condense onto the beads and it'll slowly drip down until it's evaporated again and goes up higher in the column. So keep doing that over and over again till it reaches the top.
What's the purpose of having an increased surface area?
So it's to separate the two liquids with similar boiling points. The increased surface area will force the liquids to evaporate and condense, and then evaporate and condense over and over again instead of just boiling and then reaching the top of the condenser. Like in like simple distillation, it only needs like one round of evaporation to reach the top. So this fractional distillation, it uses the fractionation column to separate the two liquids with similar boiling points. Because the liquid with the lower boiling point, it'll evaporate faster even at a lower temperature than the one with a higher boiling point. So it will reach the top of the column faster.
Mm-hmm.
Does that make sense?
Yes, thank you.
Okay, no problem. All right. Any other questions on this?
Are there ever cases where you want to separate more than two like compounds?
Yeah, so when you have more than one compound, what happens is, let's say like you have a compound at like that boils at 10, 20, and 30 degrees Celsius. So once you reach 10 degrees Celsius, the first compound will drip out, and then you might have like a little lull between 10 and 20 where like no liquid or only a little bit of liquid drips out. And then once it hits like 20 degrees Celsius, that one would slowly drip out, and then a little low until it reaches 30 degrees Celsius, and then another third compound will drip out. So pretty much you can put like basically like as many different compounds as needed, as long as there's like a good enough large enough like boiling point difference between them. So actually the 10, 20, and 30 would only work like in the fractionation column. But yeah, you can separate as many as you need. You just have to like keep replacing the flask at the end in order to ensure that you separate the different different compounds that drip out.
Awesome. Thank you.
No problem. Anything else before I give everyone this problem? All right. You need to unmute or put in the chat. Okay, so for this one, you want to separate a compound with a boiling point of 130 degrees Celsius from another with a boiling point of 134 degrees Celsius. Two compounds have similar sizes and polarities. Which separation technique would be the most effective? All right, let me start the poll. All right, take a few minutes to answer this question. All right, I'm gonna stop the poll in a few seconds if you want to get your answer in. All right, I'm gonna stop the poll now. And everyone click choice A, and yeah, that's the correct answer. So like I said before, fractional distillation, this is used when the boiling points of the compounds are very similar, less than 25 degrees Celsius apart. So since they have a boiling point of 130 and 134, you would have to use fractional distillation to separate them. Vacuum distillation, this is when the boiling points are over 25 degrees apart, but their temperatures are greater than 150 degrees Celsius. Thin layer chromatography I haven't gone over yet, but this is for compounds with differing polarities. And simple distillation, it can be used when it's the boiling points are less than 150 degrees Celsius, and also greater than 25 degrees Celsius between the two boiling points. So, yep, fractional distillation. Any confusion on this question? Okay, all right, I'll move on. So next, I'm going to go over chromatography. So chromatography is used when you want to isolate specific molecules from a large mixture of other molecules. So this uses the premise that more similar compounds will stick to each other based on like polarity or charge. And since it will stick to the surroundings, it will move more slowly. Sorry, it should say stick to them and move more slowly. So for chromatography, the sample that you want to test will be placed on a solid medium. So the solid medium is also known as the stationary phase or the absorbent. So remember that stationary, like it doesn't move, the solid does not move. And the solid is also the absorbent because it will absorb the sample that you place on it. And then the mobile phase is the phase that moves, mobile as it moves. So the mobile phase will run through the stationary phase and displace the sample as it carries it through the solid medium. It's also known as eluting. So the mobile phase will elute or carry the sample through the solid medium. So the sample will adhere to the stationary phase to a different strength based on the polarities, the chemical and physical properties, and because it will stick to the stationary phase at different strengths and move at different speeds, you can distinguish the differences between the different compounds in that mixture. So this is known as partitioning when you have the sample on the stationary phase, and the sample will separate out into the different mixture, the different molecules in that mixture. So partitioning is like when you're separating all the different compounds in that large mixture. So like I said before, since the different compounds will have different polarities and will adhere to the stationary phase at different strengths, it will elute at different rates. And this causes them to have different partitioning coefficients. So this is when you measure how far each substance travels on the stationary phase in a given amount of time as it's being carried by the mobile phase. And this partitioning will separate the different compounds on the stationary phase, and it will isolate each substance, so you can tell like which substance moves farther and which substance didn't really move at all. So there's different types of chromatography, and this is because there's different media that can be used as the stationary phase. So like I said before, the compounds will adhere to the stationary phase at different strengths depending on like the different physical and chemical properties. So if you can use like a non-polar stationary phase, and that causes the non-polar compounds to stick to the stationary phase more, and it won't travel as far as the polar phases. And the opposite will happen if you use a polar stationary phase. If you use a polar stationary phase, the polar substances will stick to the stationary phase more and won't travel as far as the non-polar compounds. So the compounds can be using the what is known as the retardation factor. So you'll most likely see it as capital RF. So the RF the RF it signifies the differences between the compounds based on the distance in the spot. The distance that the spot moved and the distance the solvent moved. So when you're doing chromatography, the bottom number, the distance of the solvent move, will be the same for each compound in that chromatography sample, but the distance that the spot moved will differ based on each different compound. So once the compound separates into the different compound, once the spot with the sample that's placed moves, it will separate out to its different compounds. So some compounds will move farther, while some compounds will barely move from that original spot. And when you take that distance that the spot moved and divide it by the amount the solvent moved, you can find the RF factor, and the RF factor is used to distinguish between the different compounds. So here's a example. So the first example is that I'm going to go over is thin layer chromatography, or also paper chromatography. So those two are very similar. They just differ based on the medium that's used for the stationary phase. So thin layer chromatography, also known as TLC, uses a thin layer of either silica gel or alumina, while paper uses cellulose. So TLC, it'll have the thin layer of silica gel or alumina attached to inert carrier sheet, most likely paper, but you'll place the compounds and not on that side with the silica gel or the alumina. So like I said before, spotting, that's when you put the sample directly onto the absorbent at the bottom. And so this sample will be placed on the stationary phase. And then once the mobile phase carries the sample through the stationary phase, it'll move it to different distances on that stationary phase. So as you can see on the right, there's 3 spots at the bottom where the samples were placed, and the 3 different samples moved to different spots on the stationary phase as it's carried by the solvent. So as you can see, 1 and 2 moved more than 3 on that first chromatography plate. So this most likely shows that the first and the second are most likely different than the stationary phase that was used, because this mobile phase was able to carry it more during the experiment, while spot number 3, it moved a lot less than the first 2 spots. So this is because the compound used on spot 3, it was more similar to the stationary phase, so it adhered to the stationary phase more, and it was carried less by the mobile phase. And then, as you can see on the right, after enough time, the solvent was able to carry the other solvents further. Then so 1 and 2 traveled more than compound 3. And further on the right, you can see the RF factor calculation. So X is distance that the compound that was spotted, the distance that moved, and then Y is the solvent front. So on the top, you can see the solvent front, that's how far the solvent moved. So as the solvent's moving, it will carry carry the spots. And if you divide the distance that the spots move by the distance that the solvent moved, you'll find the RF factor. And the RF factor can be used to distinguish the different compounds that were spotted. That's thin layer and paper chromatography. That's like the general example of chromatography. There's other types. So before I go into the other types, so I'm gonna go over how they do thin layer and paper chromatography. So like I said, after the plate has the sample spotted on the stationary phase, it's placed upright in a developing chamber with a small, shallow pool of solvent, also known as elutant. So as the absorbent is in the developing chamber, the solvent will slowly move up the TLC plate or the paper plate by capillary action. So as the stationary phase absorbs the mobile phase will carry the different compounds, and they travel at different rates based on the properties of the compound, the mobile phase, and the stationary phase. So the mobile phase is usually in an organic solvent. So this, because the mobile phase is an organic solvent that's nonpolar, the nonpolar compounds will travel farther and faster during the chromatography, because the nonpolar compounds will not adhere to the stationary phase, and since it's like the organic solvent, it will travel with the organic solvent up the plate as the chromatography happens. So the polar substances will not stick. It will not travel as much with the organic nonpolar solvent because of the differences in polarity. The polar substance will stick to the stationary phase more and will move less during the chromatography. So there's another type of chromatography known as column chromatography. So this is when you have a column filled with either silica or aluminum beads, and that's used as an absorbent for greater separation. So this is similar to like TLC chromatography, except it's on a larger scale, and you're able to separate and distinguish larger quantities of the sample. So in this type of chromatography, use gravity to move the solvent and the compound down the column. So as you can see on the right, you have a column filled with sand and glass wool at the bottom to filter the compound, to prevent any of like the alumina or silica from getting into your collection flask. But then you have the sand and the alumina to be used as the stationary phase during this chromatography. So when you pour the solvent down the top of the column, the alumina and the silica will slowly separate the solvent into its different compounds. So the compounds that are more like the solvent will move along with the solvent down the column faster and farther, while the compounds are more like the alumina or the silica. It will stick to the alumina and the silica more, and will move slower, and will not move as far. So this causes each fraction. So it will cause each compound to leave the column at a different rate, and these different compounds that drip out at different periods of time and at different rates are known as fractions. So each fraction will contain a different compound that travel through the column at a different rate. And once you collect it in the collection flask, you can evaporate the solvent in order to leave only the desired compound behind. So that's column chromatography. Next, there's another type called Ion Exchange Chromatography. So this is when you separate the compounds based on their ionic charge. So the beads in the column, instead of like silica or alumina, it will contain beads in the column that are coated with charged substances to attract and bind molecules with the opposite charge. So if you have a column full of ionic substances, it will attract the compound with the opposite charge. So if you have positively charged substances like cations, it will attract the negatively charged compounds and will stick to it and cause it to travel down the column at a slower rate. But if you have a column full of negatively charged molecules, anionic molecules, the positively charged compounds will stick to the column more and travel slower and a shorter distance. So the stationary phase is composed of a charged ion, whether positive or negative, depending on which compound of the mixture you want to separate out. So if you want to collect the positive charged compounds, you will have a column full of negative charged molecules in order to have the negatively charged molecules adhere to the positive compounds and keep it in the column, and the opposite for the opposite charge. So you can change the stationary phase based on which compound you want to collect in the column. So like I said before, anion exchange, this is when you have the stationary phase composed of positive ions that will attract negatively charged substances and keep it in the column for you to collect. So everything else will pass through, but the negatively charged substances will be stuck in the column, and you can separate it from the column later. So anion exchange is when you want to collect the negatively charged substances. This is not named based on the charge of the stationary phase. So cation exchange, this is when you want to collect the cations, the positively charged molecules. So in order to collect that, you would want to create a stationary phase full of negatively charged ions, so you can have them stick to the cations and keep it in the column. So the attracted substances, like I said, will travel in the column more slowly, and the other molecules that you don't want will travel faster through the column, and you can collect that and then put it aside. And then at the end, once everything leaves the column that you don't want, you can extract the substances stuck to the column that you are interested in. So after all the compounds move through the column, you can use a salt gradient to elute the charged molecules stuck in the columns. So you can use that to collect the desired compound stuck in the column. That's ion exchange chromatography. Lastly, there's another type called size exclusion chromatography. So this is when you have a column full of beads, and these beads have tiny pores of varying sizes. So the pores will allow smaller compounds to enter the pores and slow them down. So the smaller compounds will be stuck in the pores of the beads and will travel slower through the column. While the larger compounds that can't fit in the pores will travel faster by moving around the beads. So the varying sizes of the pores will allow the molecules of different molecular weights to be fractionated. So the larger compounds will come out of the column first, while the smaller compounds will be stuck in the pores and will travel slower through the column. So this chromatography separates the compounds based on their size. So the largest compounds will come out first, and as time passes, the smaller compounds will come out until the last compounds that come out will most likely be mostly be the smallest compounds that were stuck in the beads for a long time. So that's size exclusion chromatography. So lastly, affinity chromatography. So this is when you use a very specific substance as the stationary phase. So because you have a very specific substance as the stationary phase, it can attract that very specific substance that binds to the stationary phase. So this is the classic example is when you use a receptor or an antigen for a specific protein, or a receptor for that specific protein. So what happens is that protein of interest will be bound to the substances in the column, because you create a column with a high affinity for that protein. So affinity chromatography is very specific. Only that very specific substance will be stuck in the column, while everything else will pass through pretty quickly. So like I said before, the beads, you can have beads that are coated with receptors that bind to that specific protein, or use an antibody that binds that specific protein in order to retain that desired protein in the column. So you can see on the picture on the right, the yellow is the beads that you use in the column, and since they have specific receptors or antibodies, the targeted protein will be stuck in the column, bonded to the beads, while everything else that don't have that specific affinity for the beads in the column, they'll travel through the column pretty fast and won't be stuck in the column. So that's affinity chromatography. Any questions or confusions on this topic before I give everyone a question? You can unmute or put in the chat. All right, so I'll give everyone this question. In paper chromatography, a piece of paper is dotted with the sample mixture near the bottom and then placed in a liquid solvent. The solvent then dissolves the sample and separates the compound as it moves up the paper. So which one of these statements is correct? I'll give everyone a few minutes to read this.
Wait, I don't think the poll reset. I think it's still like.
Sorry about that. I'll start the poll now. All right, the poll should be up now. Sorry about that.
Thank you.
Thank you for letting me know. All right, I'll give everyone a few more seconds for this question before I stop the poll. All right, I'm gonna stop the poll now. Most people chose choice A, and yeah, that's the correct answer. So for paper chromatography and like TLC, thin layer chromatography, it uses a nonpolar solvent. So the nonpolar solvent will travel with the nonpolar compounds will travel with the nonpolar solvent and be higher on the paper compared to the polar solvents. So this is because of the similarities in polarity between the nonpolar compounds and the nonpolar solvent. It will travel with the nonpolar solvent, while the polar compounds will be stuck to the paper, and won't travel as far as the nonpolar compounds. And so choice B is the opposite. So that's incorrect. And then choice C and D. So paper chromatography wouldn't be able to separate it based on size. That you would need a size exclusion chromatography to separate the compounds based on size. All right. Any confusions on this problem? Okay. All right. I'll move on to the next question. Which of the following purification techniques would best separate a non-polar solute from a polar solute? All right, I'll go run a few seconds for this problem. Let me stop the poll. Okay. This should be a quick one. All right, I'll give everyone a few more seconds for this. You want to get your answer in? Okay. All right, I'll stop the poll now. Everyone chose choice D, and yep, that's the correct answer. So choice D, thin layer chromatography. It's one of the ones that separates compounds based on polarity. Choice A, size exclusion, like I said, separates it based on size. Distillation separates based on boiling point, and then ion exchange separates based on the charge of the compounds. So choice D is the correct answer. Any questions on this problem? Okay. All right, I'll move on. So last topic for today, I'm going to go over gel electrophoresis. So gel electrophoresis, it's a method used to separate different compounds based on their size and charge. So this is most commonly used to separate DNA, RNA, and different proteins. So how it works is you place the mixture of either like DNA, RNA, or proteins on the gel, and then you apply an electric field across the gel that has a negatively charged side in the cathode, and a positively charged side known as the anode. So because of the electric field and the two different charged sides, the molecule will travel through the gel to either the cathode or the anode based on their their charge, but they will travel at different speeds depending on physical properties like their size and their charge. So the larger molecules will move slower than the smaller molecules just because of the size, and then molecules of the same size that have greater charges will travel faster than molecules that are the same size but have a smaller charge. So that's just the general basis of gel electrophoresis. So gel electrophoresis usually, most likely they'll use polyacrylamide gel. So polyacrylamide gel electrophoresis, most commonly known as Page, is like the basic method for gel electrophoresis. So like I said before, you separate the compounds based on their size and or charge using an electrolytic cell. Because there's a cathode that is negatively charged and a anode that is positively charged, the cathode will attract the positively charged substances while the anode attracts the negatively charged substances. So the compounds will travel to the side with the opposite charge, and the gel separates the compounds based on their size and charge. So native Page is the most basic form of Page. This is used to analyze a protein in its natural state, so nothing is done to the protein or the DNA or RNA. The protein will remain in its native shape and maintain its secondary, tertiary, and quaternary structures, and the DNA, RNA will keep their original shape and structure as well. This separates the substances based on their size and their charge. So as you see at the bottom, that's the general setup for gel electrophoresis. You have the power source that acts as the electrolytic cell. You'll have the gel in the structure that separates the sample, and then there's wells in the gel that you deposit the sample in. And once, as you can see, the power source, it's connected to the two different sides of the gel, and once that power source is turned on, electric field will be made through the gel, and it'll force the samples that were placed in the wells to travel across the gel. So that's native Page. SDS Page, this is when you use a detergent called sodium dodecyl sulfate, most commonly referred to as SDS. So this detergent is used to denature the protein and adds a number of negative charges that are proportional to the size of the protein. And this is done to create an equal charge distribution. So none of the proteins will have greater or a lesser charge. They'll have the same charge, same uniform negative charge across the protein. This is done in order to give them a uniform charge. So you separate the proteins based on their size alone. So native Page, it separates the proteins based on charge and size. But once you use a detergent that creates a uniform charge, it will only separate the proteins based on their size. So SDS Page is when you want to just separate them based on their size alone. So SDS Page, as you can see, there you have the three different proteins on the left, A, B, and C. And after you use SDS on it, all the proteins will have a uniform negative charge across the protein. And when you run a gel electrophoresis with it, the proteins will travel across the gel. And because C is the smallest protein, it will travel farther in the gel than A or B because A and B are a lot bigger than C. So this separates the molecule based on their size alone, and the smaller molecules will travel farther in the gel than the larger molecules. So that's SDS page. So there's a form of SDS page called reducing SDS page. So besides adding SDS, that completely denatures the protein, except at places where there are disulfide bonds, you add a reducing agent that reduces the disulfide bonds as well. So the reducing agent will break the bonds in the disulfide bond, and this causes all the higher structures of a protein to be eliminated. So there are no tertiary, quaternary, or secondary structures anymore. It's just the basic primary structure of the proteins. So reducing SDS page, you add SPS and then a reducing agent to have the protein in just its primary structure. So any questions on this before I give you a question? Okay. All right, I'll give everyone this question. So which of the following is true regarding sodium dodecyl sulfate, SDS? You're on a few minutes for this question. Let me start the poll. All right, take a few minutes for this. All right, I'm gonna stop the poll in a few seconds if you wanna get your answer in. All right, I'll stop the poll now. Okay, most people chose choice D, but the answer is actually choice B. So one is incorrect because it doesn't preserve the mass to charge ratio. It changes all the charges of the proteins to negative charges, so it doesn't preserve the mass to charge ratio. Choice B is the correct answer because it does allow for the separation of proteins based on size alone, because it gives all the proteins a uniform negative charge. The proteins are separated based on size alone. Choice C is incorrect because SDS adds negative charges to proteins. And choice D is incorrect because it doesn't change the primary structure of the protein. It changes the tertiary and the quaternary structures. and it preserves the primary structures. So the primary structures are the peptide bonds between the amino acids of the protein. So it doesn't change that primary structure. It doesn't change the identity of the protein, but it does get rid of like higher level interactions in the protein, but it doesn't change the primary structure. Any confusion on this question still? Okay. If not, this is the end of the lecture for tonight. Thank you everyone for attending.